Hello everyone and welcome back. So let's do another example problem. So this is example 4.8. Now we have a simple beam, but this time we have a distributed load as well as our concentrated loads. Distributed. Everybody scream with me. Ah! Okay, we've gotten past the screaming. Let's actually solve the problem. So we want to find these support reactions, the thing that's holding it up. Now how are we going to do this? Well, it's not that bad. First off, we're going to draw a free body diagram and we're going to get rid of this load and turn it into a nice concentrated load, into a single vector. Now how do we do that? Remember, the force that this guy is exerting is equal to its area. It's always equal to its area. That's a rectangle. It's a rectangle that's 6 meters wide times 30 kilonewtons per meter high. So its area is going to be 180 kilonewtons. The second thing we got to ask ourselves is, where do we put this vector? And we always put it through the centroid, which you can look up in your textbook. It'll show you like shapes like this, and it'll have a little center point, and it'll give you some distances. In this case, a rectangle, its center is its centroid is at the center. So right through the middle. So that would be 3 meters from the side. Okay, that's not too bad. Not too bad at all. So what's the second step? Well, we're going to calculate the results in distributed load. I already did that. Fantastic. And then we're going to sum our moments about point A to start solving for our reaction forces. And then use the rest of our reactions, equilibrium equations, to solve for everything else. Now, just a little quick, very beginning question for all of you is, do you know there's going to be 2 reaction forces here? One in the vertical, one in the horizontal? Do you think there's going to be anything in the horizontal? Do you see any other horizontal forces? You don't. So most likely that's going to be 0. Now I've given you a whole lot of help on this problem. A whole lot. You should be very thankful. But I want you to try to do it on your own. I've given you the start. So pause this video. Go try it out. See how it goes. If it goes well, fantastic. If it goes terribly, practice some more. And then come on back and see how you did. If you got completely stuck, that's fine. Watch the video and see how to solve it. If you didn't get completely stuck, well, check to make sure you got the right number. Calculator errors are the biggest errors in this class. Okay, so 3, 2, 1. You went and you tried it. Hopefully you did well. And if you got stuck, well, you're back here. If you didn't get stuck, maybe you're still back here. Let's try it together. So the first part is always to draw a free body diagram. And we're going to take the distributed load and say, well, you are just a concentrated load, right in the middle. We get that from our textbook. You can look and find the centroid of various shapes from your textbook. Now what's the result of the distributed load? Well, it's the area. And so that's going to be base times height, which is 30 times 6. We already talked about that part. So we're doing pretty good so far. Now we're going to sum the moments around point A. Now why do we choose point A? Well, we could have done B, honestly, but usually we do the point that's the pin load because it usually has 2 reaction forces, just this in case we already know what one of them is. So we're going to take some of them about point A. Okay, that one right there. So these guys do not cause a moment about the point which they are connected to. And then we have to say, okay, well, everything else, what direction is it going to turn it? Well, okay, that's clockwise, that's clockwise, that's clockwise, that's counterclockwise. So I'll say that that's positive and these 3 are negative. Now moments, that is always force times the perpendicular distance. These are all vertical forces. And so the distance I need is the horizontal distance. So I need that distance, I need that one, and that one. And if you plug everything in correctly, well, I get that RB is going to be 153.8 kilonewtons. That's just me saying I'm taking the reaction force right here, times 12, minus everything else because we said they were in the opposite direction. And that should all equal 0 because we can't be spinning. It has to be in equilibrium. If it's able to move, it's no good. So next step is we know what this one is. So let's try to solve for this reaction A in the vertical direction. So we have 2 more equations. We use the sum of the moments, check. We still have some of the forces in the y and some of the forces in the x, or vertical and horizontal. So let's use the vertical forces. Now, that's vertical, that's vertical, that's vertical, that's vertical, that's vertical. This one is not, so it doesn't matter. We don't even see it. So I add them all in there. These two are going up, they're positive. These three are going down, they're negative. And I plug it in and I get that my vertical force is 161.3 kilonewtons. And if I wanted to, I could do some of the forces in the x, and I'll quickly see there's nothing else in the x direction, so that must be 0. I'm gonna go ahead and show that to you. Sum of the forces in the x is equal to 0, and it's equal to RA horizontal as I wrote it. So therefore, RAH is equal to 0. There's nothing else to push back on it, so it has to be 0. Yep, so that's it. Thank you all for listening, and I'll see you next time. Have a wonderful day. Bye-bye.